Offshore energy extraction operates in an environment where heavy steel is subjected to severe ocean conditions and volatile hydrocarbons run through every pipe. Safety regulators classify large sections of these facilities as Zone 1. This designation identifies areas where explosive gases are likely to be present in the atmosphere during normal daily operations. This creates a constant conflict for maintenance crews. To keep a facility operational, steel pipes require routine grinding and welding. However, these hot work procedures introduce high-energy ignition sources directly into areas with a high potential for combustion. The traditional solution to this risk is a full facility shutdown. Operators halt production and depressurize the surrounding pipe networks to physically remove the fuel source before striking a single arc. The financial impact of this method is immense. A single day of unplanned downtime on a Tier 1 offshore platform results in an average of $1.5 million in lost revenue. For turnaround managers, the choice has historically been binary: stop production entirely or risk a catastrophic ignition event. To bridge this gap, temporary safety structures had to evolve from passive barriers into active machines. While traditional fire blankets deflect sparks and slag, they are passive tools. They offer no protection against the migration of heavy, invisible gases into a workspace. True isolation requires adherence to IEC 60079-13. This international engineering standard reclassifies a basic welding tent into a certified pressurized room. To meet this classification, a hot work safety enclosure must simultaneously manage 3 technical variables: fluid dynamics, structural integrity, and automated deterministic control. When these 3 criteria are met, regulatory bodies allow critical hot work to proceed while the surrounding facility remains fully pressurized and online. Maintaining operational continuity requires abandoning the concept of a temporary shelter and treating the enclosure as a highly calibrated active defense system. The first defense mechanism of the enclosure relies on fluid dynamics. By maintaining a higher air pressure inside the structure than outside, the system creates an invisible, outward-pushing force. This diagram illustrates the overpressure technique. Global safety standards require the enclosure to maintain a continuous minimum differential of 50 pascals, or 0.1 inches of water column, higher than the outside atmosphere. This outward flow is specifically calibrated to repel hazardous hydrocarbons, like hydrogen sulfide and propane. Because these gases are heavier than air, they naturally pool near the floor, but the sustained pressure sweeps them away from the enclosure's seams. To maintain this boundary, the system must balance the intake air volume against the enclosure's cubic footage. If a worker enters through an airlock and causes a pressure dip, the intake fan RPM increases to restore the 50 pascal baseline. This clean air is forced into the enclosure from a verified safe zone, located a minimum of 15 meters away from the worksite via fire-retardant ducting. Pushing this high volume of air through the enclosure achieves 2 goals. It repels external hydrocarbons while extracting toxic welding fumes from the technician's immediate environment. In a Zone 1 environment, safety is not achieved by blocking gas with heavy fabric, but by repelling it through the physics of overpressure. Generating this pressure introduces an engineering conflict. The structure must be airtight enough to sustain 50 pascals, yet remain modular enough to be constructed around complex pipe manifolds in under 4 hours. The primary obstacle to maintaining this seal is constant structural vibration. Massive reciprocating compressors and industrial machinery send high-frequency mechanical stress through the entire platform. Traditional mechanical fasteners, such as zippers or hook and loop strips, are not designed for these conditions. Over a 12-hour shift, constant vibrations and 40-knot winds cause these passive materials to fatigue and lose their grip. This fatigue creates immediate danger. Data indicates that a mere 2-inch gap in a zipper-based seal allows enough air to escape that the internal pressure can plummet to 0 in exactly 15 seconds. To solve this, engineered mechanical interlocks like quadrilock panels are used. Because the panels physically interlock on all 4 sides, the joint remains airtight even when subjected to heavy industrial vibration. These panels are constructed from silicone-coated fiberglass, a material science choice that allows the walls to withstand continuous temperatures of 500 degrees Fahrenheit and intermittent exposure up to 1,000 degrees. If a single microchannel allows pressure to bleed out, the fluid dynamic defense fails. Engineered structural integrity is the necessary foundation for hot work safety. Even with a perfect seal and continuous overpressure, one variable remains: the inherent delay in human reaction time during an emergency. Relying solely on manual monitoring is insufficient in high-noise offshore environments. It can take a human firewatch 45 to 90 seconds to identify a pressure drop on a manometer and manually cut power to the welding equipment. In an explosive atmosphere, a 45-second delay is critical. It allows an ignition source to remain active while flammable gases breach the depressurized enclosure. This necessitates the use of automated shutdown systems. Systems like SafeStop utilize programmable logic controllers to eliminate human latency from the safety loop. The PLC is programmed with two critical thresholds. First, if the internal pressure drops below the critical 25 Pascal buffer, the system instantly severs the electrical connection to all hot work tools. Second, if gas sensors detect hydrocarbons at merely 10% of the lower explosive limit, the controller isolates the circuit, providing a 10-to-1 safety factor before the atmosphere reaches a combustible concentration. This automated intervention is nearly instantaneous. The logic controller terminates power to all hot work equipment in less than 0.4 seconds. Removing human observation from the emergency response is the only way to isolate an ignition source before hazardous gases reach a dangerous concentration. The enclosure only succeeds through the interdependence of these three pillars. The panels maintain the seal, the pressure repels the gas, and the logic controller monitors both variables with millisecond precision. This integration allows an arc welder to operate safely near live process units, knowing any breach results in the equipment being instantly de-energized. By 2026, global safety standards will evolve to mandate the integration of these automated habitats directly into a facility's digital permit-to-work system. This means hot work physically cannot begin unless the enclosure sensors confirm a safe, pressurized state to the central facility network. Compliance is no longer just about deploying physical equipment. It requires hardwiring that equipment into the facility's integrated safety logic. This returns us to the initial choice: halting a $1.5 million per day operation or risking a catastrophic event. Utilizing ATEX and IECEX certified enclosures removes this conflict, allowing operators to execute 48-hour repairs without interrupting production. This means abandoning basic fire blankets and demanding strict fluid dynamics, mechanical panel interlocks, and sub-second control logic. Protecting human life and high-value energy assets requires the active elimination of hazardous variables. True asset protection focuses on maintaining a non-combustible environment through engineered logic, ensuring that even in volatile Zone 1 conditions, hot work remains a strictly controlled, heavily mitigated, and routine daily task.